right? I thought there'd be data. Is anyone out there?
Welcome back. Okay, so we were talking about sufficient statistics last time. And so let me just remind you of just a couple of things, and then we won't be doing much recapping. We'll be going forward. But a sufficient statistic is, that's so awful. It's a statistic, and that may be vector valued. So it could be more than one dimensional. And if you, well, you have some model, right? So you've got some x1 through xn. So I usually write x1 through xn IID according to some PDF. But we might have the whole vector with a distribution that is given by some n-dimensional PDF, which did not necessarily have to come from multiplying individual PDFs together. They always will for us, right? So this f of vector x and theta, because we're always dealing with IID things, is just going to be a product. But it actually could be given a little more generally than that. So these things do not have to be IID to talk about sufficient statistics. Okay, so we say that a statistic S is sufficient for this distribution, for the parameter, for this model. If once you know the value of S, knowing the values of the individual x's is not going to get you any more information about theta. Statistic S is sufficient here for the model, for theta, for whatever, if once you know the value of S, the random sample is not going to give you any more information about theta. Okay, so once you know the value of S, knowing x1 through xn will not give you more info about theta. So we say that the statistic or vector of statistics is sufficient for estimating theta because you can't do any better if you had the original data. And we saw last time, no, we didn't yet. We're going to see this time that a lot of statistics are sufficient. And I didn't want you to worry about these. I mean, we are still talking about the IID case. I just wanted to write it just a little more generally since we could. Okay, so formally, to show something is sufficient, we look at the joint distribution of the x's given the sufficient statistic. And in the discrete case, we kind of looked at the probability that x1 equals x1 out through xn equals xn, given that s equals s. And we wrote that as a big fat joint probability. So all the x's and the s over the marginal probability that s equals s. And then, so the statistic s is some kind of function of the data. And this is my attempt at making like a lowercase cursive s. It kind of looks like a delta. And it's a function of the random variables. And we saw last time that this probability is 0 if the little s is not the same thing as the function of the little x's. So last time we had an example where s was the sum of all the x's, and if the little s was not the sum of all the little x's, then that probability in the numerator is 0. And for it to be sufficient, we want this guy up here to be parameter free. And so if the probability is 0, that's certainly parameter free. And then we looked at the case where little s is actually equal to s of the little x's. And then the numerator turned into, well, actually, let's just look at the whole thing. Then this joint probability, x1 through xn equals xn, and s equals s, over the probability that s equals s. So this ended up just kind of getting dropped because it was redundant information. And that is always going to happen. And the analog in the continuous setting is also always going to happen when these aren't exactly probabilities, but conditional continuous PDFs. And so this brings us to the factorization criterion due to Neyman. And I think this was the last thing we got to last time. So here we have a joint PDF, and you could have an analogous continuous joint PDF. And we want, if S is sufficient, we want this to be parameter free. If S is sufficient. And so I decided to call this some H of X, just X's only, no parameter. And multiplying this to the other side kind of leads us to the factorization criterion for sufficiency, which is stated a little more generally than this. So the factorization criterion, and this is for sufficiency, but I don't feel like writing that out because we've already seen all this. So if we can write our joint PDF as some function of X only that I'm going to call H of X, and as the notation kind of suggests, there's no theta in there, and then another function that I'm going to call G, and this allows you to have the data, the X's and the parameters mixed, but the data appears through some statistic. This should become crystal clear once we do examples. Then the statistic S, which can be vector valued, which is this S of the capital X's, is sufficient for the model. So let's see how to use this, because that was, I think, where I got last time. Let's look at an example. Let's look at two examples. The first one, how about a uniform 0 theta? I've got x1 through xn, IID uniform 0 theta. And if I'm trying to estimate theta or even any function of theta, then our common sense tells us that it's probably enough if you just remember I had a random number generator in the hallway and I had to bring in x1 through xn, and it was quite large and it was a pain. And I said, wouldn't it be enough? Wouldn't it be sufficient if I just brought you the maximum? And the maximum is a sufficient statistic here for estimating theta, and we can show it using our factorization criterion. So our joint PDF, because these guys are IID, this is a product as I goes from 1 to n of 1 over theta, and then an indicator that each xi is between 0 and theta. So I can simplify these. Well, let me write one more line here first. I can simplify these indicators in many ways. Okay, so when simplifying things to show sufficiency through the factorization criterion, it's good practice to kind of get as low dimension as you can with this thing I'm going to call the sufficient statistic. So check this out. I'm going to write this as 1 over theta to the n. I'm going to say that the maximum has to be between 0 and theta, and the minimum has to be between 0 and the maximum. So that product of indicators is going to be 1 or 0 at the exact times. The bigger product above is going to be 1 or 0, because you need everything between 0 and theta. And so if you can say the max is less than theta and the min is somewhere between 0 and the max, then you can guarantee they're all between 0 and theta. And in this particular factorization, I've got pure X stuff that I would call H of X. I would pick out the pure X stuff where there's no theta. And H of X could be identically 1. So maybe you won't see any pure X stuff. And then the rest of it together is going to make up this function G of S of the vector X and theta. And you look in that function and you see how the X's are represented. I don't need all of the X's to write this down. I just need the maximum. So this is where S is is S of X is equal to that should be a capital since I'm going to the conclusion here. S of capital X is the maximum. So the goal is to take any joint PDF and rewrite it as an X part only, and in the rest of it, look in it and see how the X's appear. In other words, what kind of statistic would you need from the hallway to evaluate G? And I can evaluate this knowing only the maximum. Yeah, so I'm going to do the minimum next. I was going to factor it differently. And yeah, I don't think this was well motivated, and I debated whether I was going to show this one first or the next one first. Let me factor it a different way and then go back to this one. So alternatively, we can take the joint PDF. This is 1 over theta to the n, the product as I goes from 1 to n of the indicators that all of the xi are between 0 and theta, and I can guarantee that all of the xi are between 0 and theta if the min and max both are. So this is equivalent to the product of two indicators. One is the minimum between 0 and theta, and the maximum between the minimum and theta. So this is going to be 1 if the min is between 0 and theta, and this is going to be 1 if the max is between the minimum and theta, and that's going to imply they're all between 0 and theta. And so this is a different way to write that product of indicators to simplify it. And so right now what I see is no pure X part. This is like identically 1. And then there's a G function, which is a function of the data, the X's and theta. And how do the X's appear? What do you need me to bring you from the hallway, from the random number generator? You need me to bring you two things, this minimum and this maximum. And so the S here, like where S is the min and the max. And therefore, by the factorization criterion, this statistic, this vector valued statistic, min and the max, is sufficient for theta, or the model. But now going back to my first example and the question on that, so I absolutely could have had like both the minimum and the maximum between 0 and theta. That would give me this function depending on both the x's and the theta. And so I wouldn't be able to pull out basically this one-dimensional sufficient statistic. But if I put the maximum between 0 and theta and the minimum between 0 and the max, I mean, that's also going to give you the same product of indicators. And in that case, that gets pulled out into the h of x function, the stuff that doesn't depend on theta, and then the part that does depend on theta only depends on the data through the maximum. One more alternate thing here for this example. Doing great with the whole words today. I can write this as 1 over theta to the n, the product as I goes from 1 to n. So I could not simplify this at all. And then if you look in there, if you leave it like this, it appears that there is no x part, no pure x part. So the h of x is identically 1 again, and this whole thing is g of some function of the x's and theta. But in order to evaluate this, what do you need from the hallway? You need each and every xi. So this implies that the statistic s, which is this weird cursive little s of x, which is the entire vector, is sufficient for this model. It's sufficient for estimating theta for the uniform 0 theta distribution. So this is why I was saying last time that sufficient statistics are really important, and yet they shouldn't be, because almost everything is sufficient. Not almost everything, but a lot of things are sufficient. If I bring you from the hallway all the data, then you can estimate just as well as if I brought you all the data. If I brought you just the maximum, you can estimate just as well as I brought you all the data. If I brought the min and the max, it's a little extra, but it's still sufficient. There is an idea of minimally sufficient that we will hit eventually. and that's going to be the lowest dimension one. We're going to do an example with 2 parameters now. Okay, and that is the normal distribution. So x1 through xn, iid normal, mu sigma squared. Now both of these are unknown, and I won't say that. I would specifically write where sigma squared is known if I meant it to be known. And so we want to find I want to say a set of sufficient statistics for estimating mu and sigma squared, but I could also say a sufficient vector. So it sounds like it's not plural, like it's a set of sufficient statistics or it's a single vector. So I'm just going to write find sufficient statistics for estimating mu and sigma squared. Or you can think of this as for estimating theta, where theta is mu times sigma squared. Because the sufficient statistic or statistics, they're not necessarily going to correspond to like this is sufficient for mu and this is sufficient for sigma squared. It's really a model thing. So let's write out the PDF, the joint PDF. I'm going to get it from a product of individual PDFs because they're IID. This is the product as I goes from 1 to n of 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared xi minus mu squared. And so this is 2 pi sigma squared to the minus n over 2. Not that you have to write it that way. You can keep it as a square root in the denominator raised to the nth power. E to the minus 1 over 2 sigma squared, the sum xi minus mu squared. So one thing I should point out is the statistic is any function of the data, and it really should not depend on parameters. It's something you can compute from the data only. So it's a little bit different than like the pivotal quantities and the things we kind of normalize when doing hypothesis testing. We started with a statistic and then we adjusted them into something whose distribution was parameter free. And those adjustments involve parameters, but a statistic should not involve a parameter. So I kind of look at this and say, I see the x's in this kind of clump. Like if someone gave me the sum of xi minus mu all squared, then that's enough for me to evaluate this. But we don't know mu. Well, that's actually, you're not allowed to have a parameter in the statistic, I guess, is the bottom line. So let's rewrite this just a little bit differently. This is 2 pi sigma squared, the minus n over 2. Just going to write exp minus 1 over 2 sigma squared. So I'm going to multiply that out. The sum of the xi squared plus mu over sigma squared, the sum of the xi, and then plus mu squared and mu squared, minus n over 2 sigma squared mu squared. And so you can break this up. So I can kind of factor out that e, that last term, e to the minus n over 2 sigma squared mu squared, and then the rest, which is just going to have the first 2 terms. And so now when I look at this, I actually don't see any pure x part unless you want to pull out, like separate this 2 pi and the sigma squared. You could say that h of x is like this constant function, like using, a function f of x equals 3. Was someone going to say something?
I think you have an exp of an e.
Oh, yeah, that should not be. Thank you. Okay, so yeah, so h of x could be this constant function, or it could be just 1. And the rest of it has the x's and parameters mixed. And if you go in there and you grab the statistics that you need to compute this, you'll see that you need the sum of the x's squared and the sum of the x's, and you can evaluate this. So it's enough to have those. So the vector s, which is the sum of the xi squared and the sum of the xi's, it doesn't matter what order you list them in, is sufficient for the model, for the normal distribution, for the parameters. by the factorization criterion, which is not surprising. It actually appears that if you want to talk about sufficient for a specific parameter, it appears that the second statistic is sufficient for estimating mu because we're probably going to estimate mu with x bar. So we won't need the squared thing. But we do need both of these together for estimating sigma squared. Probably we're going to use, and please forgive the S, this is a sample variance. Probably we're going to estimate it like this. And in order to compute that, you need these two statistics. So you can't really say this is sufficient for mu and this one is sufficient for sigma squared. You might need them both for both parameters or one parameter. And if sigma squared is fixed, then you should be able to factor this in some way that if you're trying to come up with a sufficient statistic for that model, you'll just get this guy. And if mu is fixed and known, well, then you can use mu in your statistic. So if suppose mu is fixed or known, then I can stop the factoring with, so I've got 2 pi sigma squared to the minus n over 2. I don't have to factor it at all, actually. I've got e to the minus 1 over 2 sigma squared, blah, blah, blah. And if the mu is known, then this guy counts as a statistic. Not that you have to have that. You could continue to factor this and say that you need the sum of the x's and the sum of the xi squareds. So just don't ever use a parameter in something and use an unknown parameter in something and call it a statistic. Okay, we are ready for the Rao-Blackwell theorem, one of my favorites. We got most of the work of proving this out of the way last time when we did those things with conditional expectations and conditional variances. I need a whole new board for this. So super, super exciting stuff. Gets 2 colored asterisks on both sides. Okay, so we've got some kind of x1 through xn. For us, it's going to be a random sample. Doesn't quite have to be IID. From some distribution with a parameter theta. And that theta could be vector valued. It doesn't have to be. So our goal here, I'm just going to state this sort of in bullets rather than writing out the paragraph that I need to write this out. I want to estimate either theta or a function of theta that we call tau of theta. So let's go with that. We want to estimate tau of theta. I'm going to assume I have an unbiased estimator. So an unbiased estimator, which is a statistic. And I think this will make a little more sense if I keep it in statistic form rather than call my estimator tau of theta hat. I could do that just as well. But this is some function of the x's that is unbiased for tau of theta. Okay, we're also going to assume we have a sufficient statistic S. So I'm going to define a new estimator. I'm going to call it T star because apparently it's good. So I'm going to define this to be the expected value of T given S. That's still a random variable. Remember what we talked about last time. It's going to be a function of this S, which is random. And so I can conclude a whole bunch of really cool things. It's still unbiased for tau of theta. It has a variance that's less than or equal to the variance of our original estimator T. And it will have a variance that is strictly less than the variance of T, unless T and T star are exactly the same. So let me write all that out. Then T star is still unbiased for tau of theta. Now, I'm going to make this conclusion in bullets as well. So conclusion 1, conclusion 2, the variance of T star is less than or equal to the variance of T. And then when they're equal, you actually haven't changed anything by conditioning on S. So the variance of T star is equal to the variance of t if and only if t star equals t. And I guess I'm going to put another conclusion, which is usually not listed because it's already kind of just true from this. But t star is a function of the sufficient statistic. Just by how we define that conditional expectation and our list that we went over last time, the expected value of x is a constant. The expected value of x given y equals little y is a function of little y. The expected value of x given capital Y is that same function with capital Y plugged in, which is a random variable. So I don't know, I just decided to add this, but we already know this like immediately from this definition. And let's prove the rest. And it's really quick because we've done all the hard work. So proof. The expected value of t star, what is t star? It is the expected value of t given s. And we saw this kind of iterated expectation last time. This is the expected value of t from one of those properties in a list last time. And t is an unbiased estimator of tau of theta. So therefore, t star is also an unbiased estimator for tau of theta. Stop me if that doesn't make sense. I'm going to move on to the variance then. Let's start with the variance of t as opposed to, I don't know, I have bullets everywhere, as opposed to starting with t star. The variance of t, remember last time we came up with a conditional variance formula. We can write this as the variance of the expected value of t given s plus, and now I want to reverse the expectation and the variance, the expected value of the variance of t given s. And a variance is non-negative, so the mean is non-negative. And so if I take that second term away, then I can say this whole thing is greater than or equal to the first term. But that expectation is how we define t star. So we have proven the property that the variance of t star is less than or equal to the variance of t. Okay, so we get equality of those variances if this expectation that I just dropped, if it was just zero, so I didn't have to drop it, then this line would equal this line. So we get equality if and only if the expected value of the variance of t given s is zero. Okay, but the expectation is a probability weighted average of the thing inside. And so because the thing inside is always greater than or equal to zero because it's a variance, there's no way that if you like average over all the s's that you're going to somehow get, I'm sorry, if this expectation is zero and because the variance inside is greater than or equal to zero, this forces the variance inside to equal zero. That's what I'm trying to say, because you're averaging things that are not negative and yet they average to zero. So this is true if and only if the variance of t given s is zero. Right. And so what has zero variance? What random variables have zero variance? Constants, right? So just as a little aside, if x is some constant, that's how you get the variance of x to be zero. Like there's no spread of that distribution. It'll be that constant every time. So first I'm going to say something informal, and then I'm going to formalize it. So the informal statement I want to make is, i.e., I don't know if I should put that in the quotes, but t given s is constant. That is a weird statement to make because it's a function of s. It's not constant. But if t given s was constant, then I can kind of say, so this is not rigorous. I'll make it rigorous in a moment. But if it's constant, I can kind of say the expected value of t is just t. In the same way, I can say the expected value of a constant 3 is 3. And the expected value of t given s is t star. So this is an informal way of showing that T star would equal T. But I need to formalize it because what the heck does this even mean? So this is just a one-liner. And you really need to know how conditional variance is defined. We haven't defined it yet. We just computed a conditional variance last time, but we never defined it from scratch. And we sort of use the expected value of x squared minus the expected value of x all squared formulation in conditional land. But the definition of the variance of something like t given s, the actual definition of this is the expected value of, so it's t minus its mean squared in conditional land, but all the computations are in conditional land. So it's actually t minus the expected value of t given s squared given s. This is what we usually have, it's usually like an x minus its mean, and it lives in conditional land, but the mean was also computed in conditional land. That is how you define that variance. And then if you square that out and run things through, you can get what we used last time, which was basically the expected value of t squared given s minus the expected value of t given s all squared. But from this, you can kind of easily see that this is going to be 0 if and only if the expected value of t given s is t, which is the more formal way of saying this. I don't know, I just really wanted to say t given s is constant because s is a random variable, but if it's given and known, but not fixed, how is it constant? I don't know. It's not. So I don't think I use sufficiency anywhere, but I need sufficiency in the setup of the problem because I'm trying to produce an estimator. So because S is sufficient, the distribution of the x's given S is parameter free, and that's going to make this value parameter free. So where does the sufficiency of S come in? I'm writing just as well as my sentences. Where is that? So the T star is defined to be the expected value of T given S. And if you compute that expectation, you don't have to, but I think it's easier always to start with fixing the S and then getting this function of little s and plugging the big S in. So this T is some sort of function of the data that I'm going to call T of capital X. And if you want this expected value, you would integrate T of the little x against the appropriate joint PDF. And that's going to be the PDF for the x's given S, because we're in conditional land. And actually, this is an n-dimensional integral. So this is a dx1 through dxn, and this is several integrals. So if S is sufficient, this is parameter free. And if that's parameter free, there's no parameters in the statistic. This forces, so S sufficient gives us that T star is parameter free. So it makes sense to be thinking of it as an estimator of our unknown stuff. Is parameter free, which makes it technically a statistic, but less than being the words, less than technically, we're trying to hold it up as an estimator of unknown things. And so we don't want it to be a function of unknown things. Otherwise, you'd say, I'm going to estimate mu with mu. Okay, why do we care? Why? Because if you give me an unbiased estimator of something we're trying to estimate, if I find a sufficient statistic, I could Rao Blackwellize your estimator and potentially get something better. And if it's not better, then it's the same thing. So this is like step one on our search for an UMVU to kind of like try to get lower variance and lower variance. So let's do an example though. This can be used to help you find unbiased estimators for things. So here is An example, suppose that we have x1 through xn IID Poisson with parameter lambda, and I want an unbiased estimator of like tau of lambda, which is going to be one we've seen many times now, e to the minus lambda. It's really hard to guess at one. It really is. So at this time, I should let you work in small groups and spend 5 minutes. I'm not going to do it though. And then we'll come back and I'll say, see, it was hard. So just imagine that happened. Okay, so what is e to the minus lambda? Note that e to the minus lambda is equal to the probability that any one of the x's is 0, because this would be e to the minus lambda, lambda to the 0 over 0 factorial. So what we're trying to estimate here is a probability, which happens a lot in statistics. And I can give you an unbiased estimator of any probability like this easily using indicators. So note further that the indicator of the event that x1 is 0 is an unbiased estimator of this probability. I think we've done expected values of indicators. I mean, just in case we haven't, you would take the expected value of this indicator. I think we have though. This is a random variable. It takes in only 2 values, 0 and 1. This is going to be 0 times the probability the indicator is 0 plus 1 times the probability the indicator is 1. And that indicator is going to be 1 if and only if the thing being indicated happens. So of course the 0 term goes away, and this is just a 1 over here. So we end up with the probability of the indicator being 1, which is the probability that x1 is 0. So I can easily estimate most probabilities by indicators in an unbiased way. But the thing is that this only depends on one value in the sample. So I don't think it's going to be a very good estimator because I'm not using the information from the rest of the sample. So probably not a good estimator because it ignores x2 through xn. Okay, so I am going to Rao-Blackwellize this. I usually say it much more gangster than that, but I can't say the word. I'm going to Rao-Blackwellize this B word. That's what I usually say. Okay, so to do this, I need a sufficient statistic. And so I am going to rush step 1, which is to find one. I would use the factorization criterion. So find a sufficient statistic for the Poisson. And so if you use the factorization criterion, and so try this yourself to make sure you can get this, you'll see that the statistic, the sum of the x's is sufficient for this model. Okay, and then step 2, I'm going to let my new estimator be the expected value of my first estimator given S. And we know that's still going to be unbiased for this probability. And yet it will be a function of S. It'll be a function of all of the X's. So by Rao-Blackwell, this will still be unbiased for the e to the minus lambda, which is this probability. And yet it will be a function of all the X's. So I think we'll be doing better. And plus, its variance will be less than or equal to the variance of t. And in fact, we know it's strictly less than, because if it's a function of all of the X's, it's not going to be the same estimator. Okay, so I'm just going to write one line here because we don't have time to finish this, but conditional expectations on indicators work the same. This is going to be the probability that x1 is 0 given S. And the way I would work this out is I would fix a little s, right? I would consider this expected value given s equals little s, and that is going to be the probability that this thing happened given s equals little s. And then I'm just going to go. It's very similar to what we did when showing sufficiency, right? We can write this as the joint probability over the probability that s equals s, and we're going to go. And in the end, we're going to get a statistic you've already seen. So after some work, we're going to get n minus 1 over n to the sum of the x's, which you actually saw in one of your homework problems was an unbiased estimator for e to the minus lambda. So sometimes you can easily guess at unbiased estimators based on just one statistic and then try to build it up and get the rest of the data in there, and that will bring down the variance. And next time we'll see if we can't bring the variance all the way down. Thank you.